appreciate very much my presence here. I thank Andreas for the invitation to give this talk. And the idea today is to give some general accounts of the research we are doing in our lab, involving graphene materials, graphene-based materials, and also we'll think about some applications, some recent examples of investigations we are doing in our group. So I will start with, here's a brief outline of my talk. Sorry. Yes. I'll start by giving some general information about our group, and then I move to discuss structure and background information on graphene and graphenic materials, and finally move to some applications and examples of recent investigations. We are located in Vitória, as André said. We are in the southeast region of Brazil, close to the coast, not far from Rio de Janeiro. It's one of the most known cities in Brazil. Here is our university, Universidade Federal do Espírito Santo. We are pretty close to the beaches, to the airport, so it's a pretty convenient location. Of course, everybody is welcome to visit us at any time, especially in the summer. Vitória is a beautiful city during the summer. Our laboratory is located here. Here is the campus, main campus of the university. Our laboratory is here. And we are close to a center of containing research facilities. Is named the Center of Competence on Petrochemistry. This is the main building where our instrumental facilities are located, including our NMR spectrometers. Most of the results I'm going to describe today and tomorrow in another talk are recorded in these two, especially this one, this spectrometer, high-field NMR spectrometer. In our group, we study different types of materials, including carbon materials derived from lignocellulosic precursors, and porous materials of different types, biochar. And more recently, we started some 5 or 10 years ago, we started to study these graphenic materials, especially graphene oxide, reduced graphene, and hybrid materials. We use a lot of different characterization methods, mainly solid-state NMR, as I just mentioned, but also some other spectroscopic methods, measurements of physical properties, and so on. Here are some of our current projects involving biochar, nanocomposites, studies of porous carbons applied in discussion catalysis and electrochemistry, including our work here with Andreas. Some studies involving solid-state NMR analysis of lignocellulosic and graphene-related materials, and part of our group is devoted to computational studies of materials and other types of porous materials. Our group is composed of a good number of senior researchers. I believe some of you here will recognize this name, Professor Emerick. He was the founder of our group, one of the main names in carbon research in Brazil and Latin America. He's retired now, but still active in the lab. We have a good number of students of chemistry and physics, and in collaboration with several groups around the world. So the idea today is to talk about graphenic materials in a broad sense. I will define later exactly what I mean by this expression, graphenic materials. So these materials have applications in very different sectors. Some of them are indicated here, and all these materials share a common structure unit, which is the graphene layer. So I'll show some slides here about graphene, about the material, the single layer of carbon atoms that was the subject of the study of these two guys, Undergard and Kostya Loposelov. They worked in the University of Manchester, and in 2004 they were pioneers in the isolation of graphene layer. And for this work, they were awarded the Nobel Prize in Physics in 2010. And essentially what they did was to isolate some graphene layers from a piece of graphite. I will show the method later. And more than obtain the material, they studied the electronic properties of graphene. This is one of the first papers where they demonstrated the electronic properties of graphene devices. Here is a picture of the device they used with some, this is the graphene fragment, these are the gold contacts. And with this type of device, they were able to study the electronic properties of the material, especially, to show here, this type of measurements. This is known as the electric field effect, how the conductivity of the material changes when you apply a biased voltage. Since then, a large number of investigations have been carried out around the world involving the study of properties of graphene. So graphene is known today, since many years ago, as one of the top materials in terms of physical properties. It has extremely high thermal conductivity. It's extremely strong but flexible at the same time. It has high electromobility, and all these properties combined make this material unique for different types of applications. I'm going to show some examples of these properties later. Here I shows the evolution in the number of citations of the wood graphene papers, cited papers, and of course after the work of Gaia and Novozalov, this number showed an enormous increase. But it's interesting to note that even before their work, the concept of graphene was already present in the literature. So not as an isolated material, but as a component, as part of the structure of carbon materials. And here is the conventional picture we use to describe graphene and the other carbon forms. So graphene is this single layer here, single layer of carbon atoms joined by 3 bonds, and with a high degree of electron delocalization throughout the layer. From graphene, you can construct the structure of other carbon materials such as graphite, fullerenes, nanotubes, and many others. So in certain way, graphene can be considered, as it's written here, the mother of all graphene forms, of all carbon forms that share this structure unit. Not only the crystalline forms, but also the disordered forms of carbon, of different types of carbons can be described using the concept of graphene as a structure unit. So these are it's called the tubular structure carbons, three-dimensional material. These are carbon blacks. And if you look closely, we recognize the presence of graphene layers, even containing a large number of defects, structural defects. These layers are present in the structure of these materials. Of course, not all carbon materials are graphenic. We can have materials such as amorphous carbon, such as diamond, where the coordinations of another type. These are tetrahedral materials. But our focus today here, it's only graphenic materials. The tubular structure materials are composed by these crystallites, these small crystallites. Within the crystallites, we find the graphene-like layers. These crystallites are disordered. They are arranged in a disordered way, so the structure is high porous, and there are a large number of crosslinks. This picture here is a model from a paper published by Prof and Franklin in the 1950s. So it's a drawing, of course. But nowadays we can almost see these crystallites in high resolution images such as this one at the left, where I show the image of a disordered carbon compared to a graphitic carbon. And these structures can be also modeled using atomistic simulation methods, such as molecular dynamics. This is a powerful method to understand the structure, the evolution of the structures as a function of methods, and to calculate the signatures of different sites in the material. I'll talk a bit now about the nomenclature, the terminology. The word graphene has been used in a lot of different contexts, including scientific papers, advertising, such as this one. And in many instances, the word is used to mean different things. In this case, for example, they are saying this clothes is composed of graphene. Of course, they are not talking about singularity in this case. They're talking about the presence of graphene in materials. Also, if we can buy some commercially, some packages of materials labeled as graphene. This is a bag we received in our lab some years ago, labeled as graphene with enormous number of layers. This is a black powder. It's pretty much similar to graphite. So this is not graphene, it's not single layer graphene, of course. The fragments, the particles contain fragments with graphene, but these are not pure single layer graphene. This confusion also appeared in the literature. You can find several papers where the word graphene appeared in the title or in the abstract. And when we look more closely, we find some examples of three-dimensional materials, disordered materials, triple structure carbon. Even in papers published in Carbon and on other high-impact journals. So I'm going to use here the terminology recommended by the carbon community. This paper was published in 2013, many years ago. But unfortunately, the recommendations had not been completely adopted by the scientific community. So in this terminology, graphene, the word graphene is used to define a single layer of carbon atoms connected by sp2 bonds. When we refer to materials containing graphene layers, we can use some adjectives such as multi-layer graphene, a few layer graphene, bi-layer graphene, or even graphene-based materials when we refer to materials such as this two, graphene oxide, reduced graphene oxide. Or more broadly, we can talk about graphenic materials when we mean structures such as this one, which is a three-dimensional structure. It contains graphene, but it's not graphene. So I try to use this terminology when referring to our materials. In our lab, we work with these type of materials. We do not produce single layers of carbon. We do not produce graphene layers, graphene materials. In terms of structure, in graphene, we have carbon atoms exhibiting sp2 hybridization. So we have 3 orbitals responsible for the sigma bonds and 1 orbital, pi orbital, where responsible for the electron delocalization. So in graphene, we have a high electromobility associated with these orbitals, the pi orbitals, whereas the sigma bonds are responsible for the strength of the material. These electrons in the sigma bonds do not participate on the low energy excitations, on the thermal process or the electrical process. Only the pi electrons take part of these processes. From the crystallographic point of view, the graphene lattice can be described using this combination of 2 Bravais lattices. These are 2 interpenetrated triangular lattices generated a honeycomb structure, which is the name of this type of arrangement. So we have 2 points per unit cell. And the first Brillouin zone, where the energy excitations are more properly described, is composed by this hexagon. We have here these two high symmetry points, K and K prime. At these points, they are known as the Dirac points. At these points, the energy bands meet. So we have here a lower band, and describe it as a valence band, completely filled, with states completely filled, electronic states filled, and above it, we have a conduction band completely empty. And these two bands meet exactly at these points. These are the vertices of the hexagon shown in the previous slide. And around these points, if you make an expansion of the energy versus wave vector relation, the so-called dispersion relation, we find a linear relation between energy and the magnitude of the wave vector. This is completely different from what we find in normal semiconductors, in 3D semiconductors, for example, where this relation is. This type of linear relation is responsible for many of the electronic peculiar properties of graphene that are responsible for most of the properties I have mentioned before. And by the way, this type of relation is similar, mathematically speaking, is equivalent to what we find for photons in relativistic physics. So there are some interesting similarities between the behavior of carriers in graphene and the behavior of relativistic particles. But of course, with a completely different value of the velocity. This is the electric field effect I mentioned in the beginning of the talk. When we apply a gate voltage, we can inject electrons or holes, and then the conductivity of the material will increase significantly. That's the main effect discovered or demonstrated by the Manchester researchers in 2004. And this can be easily explained if you consider these Dirac points, the form of the linear dispersion relation around these Dirac points. Also, the optical properties of graphene can be calculated using that model. It's possible to show that graphene has a high transmittance. The absorption coefficient is about 2.3%, and it changes very little for different wavelengths. So the material is practically transparent. It's a conductor and it's transparent. These two properties combined allow the application of graphene in different types of optoelectronic devices. So it's possible to look at graphene, to visualize a graphene layer because of this tiny amount of absorbed light. I will move now to discuss some production methods of graphene. In the original work by Guy and Lovoselov, they used a type of exfoliation method, mechanical exfoliation method, which is the traditional way to obtain graphite flakes and graphene layer. This is pretty much the same thing that occurs when we draw and write with a pencil. We produce fragments of graphite, and among these fragments, we can find some contributions of layered graphene. The method they used was to take some Scotch tape, and by repeated peeling of a piece of graphite, HOPG, highly oriented pyrolytic graphite, they were able to produce these fragments and transfer the fragments to a substrate, and then by carefully looking at these images, they were able to identify some fragments containing the single layers. Here is a picture of one of these layers they obtained in 2004. So this is the method most used to produce good quality, but in small amounts and with quite reduced size. The layers can be identified by using STM, for example, as shown in this slide. But probably the most useful method to identify single layer and few layers of graphene is Raman spectroscopy. You can see here that the Raman spectrum of a single layer has some features. So especially the identification of this band here, it's known as the 2B band. The identification of this band is a powerful way to determine the number of layers in the material. Apart from the mechanical exfoliation, there are many other methods to produce graphene from carbon precursors. Probably the most used method to produce samples of high quality and in large size is chemical vapor deposition. So by using CVD, it's possible to produce samples of large sizes and good crystallinity. And these are the samples used in the multiple applications in photonics, in electronic devices, and in transistors, and many other types of applications. So traditionally, CVD use a hydrocarbon gas, and the material is decomposed, and the graphene is deposited. The layers are drawn on a metallic substrate such as nickel, copper, or others. Here I show some examples of deposition of a single layer and some few layers of graphene over metal substrates. It's also possible to use this CVD method starting from solid sources. So instead of using hydrocarbons in the gaseous phase, the group of James Stewart proposed many years ago to use some biomass or other carbon sources in a reactor by heat treating the material at high temperature. They demonstrated the possibility of producing graphene by a method similar to CVD, but starting from solid sources. In this paper, they show many examples of cheap sources of carbon, such as wastes, chocolate, cookies, etc. And they produced a very beautiful Raman spectrum containing this 2D band and the absorption expected for single layer graphene using these low-cost precursors. It's important to understand these methods and to improve these methods if we think about the mass production of graphene. So CVD starting from this cheap source may be a good alternative for the mass production of graphene, as well as these methods here, the liquid phase exfoliation. Liquid phase exfoliation is a method that allows the production of graphenic materials, not just single layer graphene, of lower quality in comparison with CVD. So the crystallinity is inferior, the sizes are much smaller, but these materials are cheaper, and they can be used in different applications involving, for example, coatings, inks, and they are used for the production of electrodes and many important applications. So I will describe now the sequence of some of these liquid phase exfoliation methods. The most known of these methods is the graphite oxidation. The production of graphite oxide is the reaction that has been known for more than a century. We prepare mixture of graphite, potassium permanganate, and in acid medium, and the reaction is carried out at temperatures just above room temperature, and after intercalation and expansion, eventually you can suspension of graphene oxide layers. These suspensions are very stable over time, and if you dry this material, you can obtain a powder known as graphene oxide, that can be later reduced to reduce graphene oxide. So this is what we call graphene oxide. It's a layer of graphene containing a lot of oxygen functional groups. And this material is the result of the graphite oxidation I have just described. We can characterize this structure using different methods, especially in our group. We use a lot this solid-state carbon titanium NMR, which will be the subject of another talk tomorrow. So we can characterize the presence of these oxygen functional groups and also see the signal due to the sp2 carbons. And more importantly, we can follow the reduction process. So this graphene oxide can be reduced to graphene. The pristine graphene structure can be recovered. Although with some defects, it's impossible to get rid of all defects. So this is not exactly graphene, it's reduced to graphene oxide. But this reduction process can be followed by using solid-state NMR as well as other spectroscopic methods. So this is a method to produce a material with good thermal conductivity, good electric conductivity starting from graphite and using a reaction in liquid medium. Here are some pictures of reduced graphene oxide. You can see here the sheets, folded sheets. This corrugated morphology is typical of these graphenic materials. And then here are some spectra, NMR spectra and XPS spectra showing the reduction process. Graphene oxide with a lot of oxygen functionalities, and this reduced graphene oxide with an increased contribution due to the sp2 carbons. One of the advantages of this method, apart from its simplicity, is that it's possible to functionalize the material. Since the reactions are produced in liquid medium, it's pretty easy to functionalize these materials. For example, in this paper, we did this functionalization with amides, and we followed the incorporation of these nitrogen-containing groups by using solid-state NMR again, and these materials were later characterized by electrochemical measurements and showed good improvement in their electrochemical performance. The exfoliation, liquid phase exfoliation, can also be conducted without oxidation. Exfoliate graphite in aqueous medium by using some surfactants. This method has been proposed many years ago, especially by the group of Professor Jonathan Coleman from Dublin. They simply mixed graphite with some surfactants, detergents, and using a kitchen mixer, they were able to produce a lot of aggregates, or graphite aggregates, and among them, they were able to identify the presence of single layer graphene, again characterized here by Raman spectroscopy. So this is an easy method, low-cost method that allows the production of graphene. And at this point, I'd like to make a small intermission because this method can also be used for the production of other 2D materials. So just 1 year after the publication of the paper dealing with the electric field effect of graphene, the same researchers demonstrated that other 2D materials could be obtained by the same exfoliation methods. So there are nowadays many types of 2D materials that can be produced by mechanical exfoliation, by liquid phase exfoliation, not the same way, similar way as I described for graphene. Some of these materials are semiconductors, so different from graphene. Graphene is a semi-metal. The band gap is 0, which cannot be interesting for some applications in semiconductor devices. So other 2D materials, such as the chalcogenides, they exhibit some band gaps, non-vanishing band gaps. So depending on the number of layers, you can have band gaps with different values engineered by playing with the number of layers of the 2D materials. These layers can also be arranged, so you can use a method such as layer by layer deposition or something like that to produce heterostructures of these layered materials, one on the top of the other. These heterostructures are known as van der Waals heterostructures because the coupling between the layers is dominated by the van der Waals dress. In this paper, they demonstrated the possibility of production of devices involving the deposition of several layers. Here is this heterostructure containing graphene and boron nitride. But there are many other examples that you can find in the literature. The exfoliation using surfactants is not possible for these materials. This is another paper by the Coleman group showing stable suspensions produced by liquid phase exfoliation of all these materials here. And the presence of the 2D fragments is evidenced here by using these microscopic methods. Coming back now to graphene, I'm going to show a few slides about the mass production, the production in large scale. Of course, the mechanical exfoliation is a good method, but just for using the lab. So if you want to upscale the production, it's necessary to use methods such as CVD or this liquid phase exfoliation. Nowadays, it's possible to find commercial equipment such as this one in a semi-industrial scale. These instruments can be used to exfoliate graphite and to produce the distribution of graphene layers in solid form. Some years ago, this paper was published, making a good review of the different types of graphenic materials produced using this liquid phase exfoliation in large scale. And they concluded, the analysis is very complete. One of the conclusions was that the materials are composed of different distributions of particles containing a number of aggregates with different numbers of graphene layers, and the quality of the material is highly dependent on the methods, the type of instrument used, and the methods used to produce the exfoliated material. So that example I showed in the beginning of the talk, probably this is also produced with a machine such as the one shown in the previous slide. Of course, this is material containing a heterogeneous distribution of particles with different numbers of graphene layers. Commercially, you can easily buy graphene samples online. For example, this is the graphene supermarket. You can find fragments, you can find some graphene oxide samples, and even the exfoliated fragments can be easily bought online. This price probably are outdated, but the offer of these materials is abundant nowadays. And we have many companies that produce graphene using this exfoliation method. I will show here some examples of Brazilian companies that I know that I'm sure these companies can be found in other parts of the world, of course. This is a company located in Caxias do Sul, not far from the border here with Uruguay. It's UCS Graphene. They produce graphenic materials using liquid phase exfoliation for applications in electrodes and among others. This is the MG Grapheno. It's a project conducted in the Universidade Federal de Minas Gerais, UFMG, also in southeast Brazil. They produce few layer graphene, and they have a lot of expertise with the characterization of this material using Raman spectroscopy. And here it's a company in São Paulo. It's a company associated with the university, the Mackenzie University. They follow this MacGraph project. They produce graphene aerogel among other types of graphenic materials using liquid phase exfoliation and other similar methods. So I will now to describe some applications of graphene and graphenic materials and show some examples of things we are doing in our group. As I mentioned in the beginning, graphene combines good electrical conductivity, good electromobility, especially high thermal conductivity, and it's a transparent material. So the combination of these properties allow the application of graphene and of graphene materials in different sectors, especially those involving optoelectronic devices and high frequency transistors. So here is an example of a graphene sheet used as a transistor, especially in the range of terahertz, which is a high frequency range below the optical range. It's possible to produce these devices based on graphene that give a good response in this frequency range. And from the optoelectronic point of view, graphene can be used for the production of touch screens, smart windows, solar cells with different resistances. The electrical resistance of the chip is the key factor that determines type of application of these materials. In this case, they use the sheets of graphene produced by CVD, especially by CVD, where the quality is higher, and the quality will determine the electrical resistance of the sheet. Since graphene is also flexible, it's possible to fold the sheet. A promising field of application of these graphene-based devices is in the construction of wearable electronics or foldable screens, such as the one shown in these examples here. Graphene can also be used, and graphene materials particularly can be used for the production of inks and filaments to be used for 3D printing. In this case, the quality of the material, the crystalline quality of the material is not the most important factor. So for this type of applications, it's possible to use the graphenic materials produced by liquid phase exfoliation. It's possible to find these products in the market. It's easy to buy this filament that can be used to produce objects with the shape that you might desire. And this this type of method can be applied, for example, for the development of artificial organs or of electrodes to be used in the construction of batteries or capacitors or other devices such as this one. So 3D printing is one of the fields where graphenic materials find a large number of applications. Another field is membrane, the production of membranes. Graphene oxide is synthesized for solution, aqueous solutions or aqueous suspension. And when this material is dried, naturally the layers tend to deposit one on the top of the other and to form a membrane. These membranes have good mechanical resistance. They are strong, and they can be used, for example, for desalination, for the purification of water. The permeation rate of ions through the graphene oxide membrane depend on the radius of the ion. So you can separate present in water solutions by using this method. And in this paper here, the authors demonstrated that it's possible to tune the interlayer spacing between the graphene oxide layers by changing the moisture content where the material is stored. So you change the water content, the water molecules are intercalated between the layers, if you change the water content, these layers can the interlayer space increased or decreased. So they can tune the permeation rate of different ions by playing with this interlayer space. Here are some examples of the application of this method with different interlayer spacings. We find the different permeation rates for ions of different sizes. So the use of geomembranes is a very strong field of application of graphene oxide. This is a different type of application. It's an important application, especially in the region of Brazil where I live. There are a lot of mosquitoes over there. And these authors here showed that graphene oxide membranes can act as mechanical and biological barriers to avoid these insect bites. Depending if the film, the geofilm, is wet or if it's dry, the barrier can have just a mechanical effect, or it can have a biological effect, avoiding the passage of molecules here that could attract the insect, the mosquito in this case. So, for example, when they use the dry geofilm, they obtain essentially no bites. The mosquito simply did not get into the tissue. In case of wet geo, the performance was not so. So this is an interesting different type of application of geomembranes as biological barriers. And during the last few years, different types of applications of graphenic materials like tensors also happened. This is an example involving the detection of the SARS-CoV-2 virus. They use the type of functionalization of a graphene layer to induce an interaction with the virus spike protein. And with this, they were able to build a device that was used and showed good performance for the detection of the presence of this virus. Here you can see the increase in the detected signal, in the magnitude of the detected signal for samples collected from patients with COVID affected by the COVID, the SARS-CoV-2 virus. Also in the field of biosensors, I'm going to show now some examples of works conducted in our group or by colleagues in our university in the field of biosensors. This group here is led by Professor my colleague at UFES. They demonstrated by computational methods, theoretical work, that a heterostructure containing graphene and boron nitride, hexagonal boron nitride, could be used for the detection of DNA and for the identification of nucleotides. So they constructed a model containing a big bore here. Here we have graphene, boron nitride in the top and the bottom parts, and the central region we have graphene. And when the DNA molecule passes through this pore, the electronic properties of the device are changed. And they demonstrated that depending on the type of the nucleotide, you can have slightly different responses. So the device is selective, can be used to detect different nucleotides in a DNA molecule. So applications of graphene and graphenic materials, sensors, biosensors, or electrical chemical sensors, or even mechanical sensors, these applications are very common. I'm going to show another example in the field of electrochemical sensors. This work was produced by one of my former students. She used the spent lithium-ion batteries to recover graphite and from the anode and lithium cobalt oxide from the cathode. And after some processing here, she produced a hybrid material that was used also as an electrochemical sensor. We did the thorough characterization of the material. These are the solid-state NMR spectra, the GO produced from graphite, from the recycled graphite, the RGO, and the hybrid material. You can see that in the case of the hybrid material, all carbon atoms have the same chemical environment. These are sp2 carbon atoms. And by looking at the XRD patterns, we could recognize the presence of cobalt oxide. So this hybrid material is indeed a composite containing cobalt oxide and reduced graphene oxide, and also contains some lithium, used solid-state lithium NMR to look at the presence of lithium. Of course, this material was recovered from lithium-ion batteries, so it's not surprising that we still have some lithium content in the material. And later she demonstrated that this material could be used as an electrochemical sensor. As an illustration, I show here the voltagrams obtained with ascorbic acid solution. So can construct a beautiful calibration curve and use this material as a sensor for the presence of these substances. Have also done some works in the field of optical applications. Here we use graphite oxide, pretty much the same as graphene oxide in the solid form, to modify parts of an optical fiber to produce pulsed laser. The relative property here is the saturable absorption that characteristic of graphene and graphene oxide. So due to this property, the existence of a geo layer here allows the production of these pulses with well-defined width and good output power. And the last few years, we are working also with the production of graphene quantum dots, starting from graphene oxide. Graphene quantum dots have photoluminescent properties. They can be used in fluorescence microscopy, for example. And we use the graphene oxide as a starting point to produce this graphene quantum dots. This is just the characterization of graphene oxide. You see here the typical XRD, the typical diffraction peak of graphene oxide, the typical solid-state NMR spectra. And this material was taken to a hydrothermal reactor. In this case, it's a common reactor. And by heat treating the material at temperatures in the range between 120 and 175 degrees, we could produce these graphene quantum dots observed here by TM. And the fluorescence of this material, of these materials, was investigated. Here I show the examples of the pictures taken under ultraviolet light irradiation. You can see that the samples indeed exhibit fluorescence, and of course the fluorescence spectrum showed a maximum here of the signal after irradiation, again on the UV. Just for comparison, this is the graphene oxide, the precursor. So the properties indeed related to the formation of these confining systems that we call carbon dots, or in this case, graphene quantum dots. Probably also, I think this is the last example. I show here some a combination of computational and experimental study about the incorporation of phosphorus in the structure of graphene oxide. Phosphorus can be incorporated by different methods in the structure of graphene oxide. In this work here, we simply played with mixtures of sulfuric acid and phosphoric acid during the synthesis. And by playing with the volumes of these two acids, we were able to produce some samples containing good amounts of phosphorus Here I show the solid state phosphorus spectrum of the sample produced using different amounts of the two acids. Here are the contents, the phosphorus contents. They are about between 4 and 5% in the pit. And the oxidation degree that we can determine by looking at these lines here, the resonance associated with the oxygen functional groups, the oxidation degree is also high for these samples. So around this range of volumes, we could produce significant amounts of phosphorus. And then when we moved to the computational part, we went to try to understand how the phosphate groups, the phosphoric acids and the phosphate group interact with the graphene oxide groups. So we constructed a set of models involving the interaction of phosphoric acid with the graphene and also with graphene oxide. We calculated the energies, the conformations, the distances of the relaxed structures, and finally we calculated the chemical shifts. So it's possible to calculate the shielding, its nucleus, and the chemical shift associated with its nucleus. And by looking at the different models, we determined what types of interactions were more likely when compared to the experimental spectrum. So I used NMR spectrum as a verification tool to understand how the interaction between phosphorus and graphene oxide occurred. Based on these results, we proposed some models for the interaction of phosphoric acid and phosphate groups with graphene oxide. Here is a 3D view of the model. The interaction involves a lot of hydrogen bonds because graphene oxide has a lot of water molecules intercalated between the layers. So this type of model is compatible with both the NMR results, the carbon-14 NMR results, the phosphor-13 NMR results, and with the calculations. Just to finish up, I'll present here a couple of ongoing projects. In this case, we are trying to modify the functional groups on graphene oxide to allow the production of electrodes that can be used for the identification of substances present in coffee. The state where I live, Espírito Santo, is one of the largest coffee producers in Brazil, especially of a variety of coffee known as Robusta or Cotillon. And we plan, it's a project, it's still a project, we plan to use computational methods to optimize the interaction between the functional groups of graphene oxide and these substances present in coffee, such as caffeine, terpenoids, and chlorogenic acids and others. And these materials then will be used for the electrochemical detection of these substances. Hopefully, our plan is to arrive at a method for classification of coffee to identify the composition and perhaps classify the coffee samples according to its origin. Another application that we are studying now is the use of graphene oxide, reduced graphene oxide, in composites with cellulose, with nanocellulose, to produce materials that can be used as flame retardants. So this material resists. There is a movie here. I don't know if I'll be able to play it. Let me try. So the material, yeah, it works. The material simply doesn't burn. I mean, just the surface is burned by the combustion, and after the beginning of the process, a charge is formed around the surface. It just protects the layers underneath, so the flames do not propagate. That's the idea of the flaming retardant. So there are some researchers in our group working with the development of this products involving RGO and cellulose nanofibers. Sorry. Okay. I leave a large number of references here for those who are interested in getting more information about these subjects. I'll put all the slides in my website. I'll leave the address here in the end. So if anyone is interested in reading more about these subjects or in get more information about any of the applications, there are lots of references indicated here. All these slides, as I said, will be available at my website. So to conclude, I'd like to thank my institution, Universidade Federal do Espírito Santo, Laboratório of Carbon and Ceramic Materials, and also Universidade da República, Comissão Setorial de Investigação Científica for supporting my visit here, as well as to FAPES, who also helped me to be here. These are my contacts, so I leave everything in this website if anybody is interested. And our group also has some channels, Twitter account, YouTube account, where all the information can be found, including some postdoc opportunities. Thank you all for your attention.